Alright, so we're now going to move on to another part of differentiation, which refers to stationary points. So as you can see in this question, the words stationary points are actually referenced, and for many of you this may look pretty unfamiliar. So let's first read the question. Find the stationary points of the curve y equals 2 plus 3x minus x cubed and determine their nature. Okay, so the first thing we need to find is stationary point. So a stationary point is actually like a critical point almost. So let's take the curve y equals x squared. Let me just draw a simple xy plane. Pretty simple. This here is the curve y equals x squared. Now we can see that y equals x squared has a minimum point here, which means that like the point at which y cannot be any lower. So y and y equals x squared cannot be lower than 0. Which makes sense because if you plug in any value of y, even if it's negative, it'll be squared, so it'll become a positive number. So 0 is the lowest one it can be. So 0 would be, well, the point here exactly would be 0, 0, because if you put x to 0 in there, it becomes 0 squared, which is just 0. So the point 0, 0 in this curve, the y equals x squared curve, is a minimum point, because the graph cannot get any lower than 0, 0. So you can typically see it's like this sole point just sitting over there. Now, let's consider another function. Let's consider something like this. And this is exactly the opposite. This is y equals negative x squared. And we can see that it has a top value here, and it doesn't go above. So this is referred to as a maximum. In this case, it's also 0, 0. So over here, 0, 0 is considered a maximum point because the graph cannot go any higher than that. All right, and let's consider one final one. Let's say we had a curve that looked more like this. This here is y is equal to x cubed. And this looks a bit different from all of them. You can't see a distinct point at which it's different, right? However, we can see that over here at 0, 0, the graph kind of like becomes less steep, but then becomes more steep again. So it like changes almost. It looks a bit odd. This here is referred to as an inflection point, a stationary inflection point. So we can say in the y is x cubed, 0, 0 is an inflection point. So these are the three types of stationary points we'll look out for. Maxima and minima are more obvious, but inflection points are a little bit more difficult to discern. But the main thing to notice is that inflection points, they consistently stay with like the gradient at points. So what I mean by that is, let me just draw this again. Okay, so let's look at a maxima. So that's a maximum. Well, let me draw that again. That's a pretty bad one. Yeah, that here is the maximum that we were talking about, y equals x squared. How can we tell it's a maximum? Well, basically, on the graph to the left of the maximum, like this side of the graph, the gradient at one specific point, let's say we take a point just to the left of the maximum, it should be a positive gradient. And as you can see, it is, because it goes like that. And if we relate this to our tangents and normals unit, basically, if we're calculating the tangent at a specific point, it should be a positive one. On the flip side, just on the other side, to the right side, it should be a negative gradient. And it should be sloping downwards. But the thing is, we don't actually need to find the distinct tangent of each like point next to it. We don't actually have to go through all that working. What we can do is construct something known as a sign diagram, which I'll go into in more detail. But first, what I should do is clarify how exactly you find the stationary points. Well, you use something called the first derivative test. And I'm going to show it over here. So let's take a look at this example. Find their stationary points of the curve y equals 2 plus 3x minus x cubed and determine their nature. So the first thing we have to do is differentiate the equation once. that's known as the first derivative, what we get left over, because we're just differentiating it once. So dy over dx is equal to, so 2 just becomes a 0 because it's a constant. 3x becomes 3, and x cubed becomes, negative x cubed becomes negative 3x squared. Also, you may be wondering, there are more than one derivatives you can do? Well, yes, and I'll show that in the next video because that will make actually using maxima and minima so much easier. Although you should approach those kind of questions with caution because the second derivative test is prone to errors. Anyway, I'm sure this makes no sense yet because we haven't actually even talked about what that is. So let's just concentrate on finding the stationary points of the curve. So the next step we have to take is making this expression, the first derivative, equal to 0. So 3 minus 3x squared is equal to 0, which we can factor to become 3 times 1 minus x squared, which is equal to 0. So now, as we can see, x can be 1 to make this expression 1, or it can be negative 1. So those are our two x coordinates for this curve that we can see that are stationary points. So now we just need to find the y value of each of these x coordinates. So when x is equal to 1, y is equal to, now we just plug it into the equation over here. So 2 plus 3 times 1 minus 1 cubed. So that's 2 plus 3 minus 1, which is 5 minus 1, which is equal to 4. So our first coordinate is 1, 4. And now our other one, where x is equal to negative 1, our y coordinate is equal to, so it's 2 minus 3 and then plus 1. So 2 minus 3 is negative 1, plus 1 is 0. So our other coordinate is negative 1, 0. So we've done the part where we find the stationary points. Now we need to determine their nature. And determining their nature basically means we have to find whether it's a maxima, a minima, it's a maximum, a minimum, or an inflection point. So the way we do this is, as we saw with the maximum, a maximum needs to have an ascending gradient before, and then a descending gradient when we have like a curve like this. Whereas a minimum point needs to have a descending gradient at first, and then an ascending gradient. And an inflection point, which looks something like this, just needs to have a consistent gradient. So it can be either positive and positive, or it can even be the other way. It can be like negative and negative. But it has to be the same thing with the inflection point. With maximum and minima, it has to be different. So what we can do here is plug in values before and after the maximum and minima. So let's take the first one, 1, 4, the first coordinate. So let's look at the points where x is 0 and y is equal to 2. So sorry, when x is 0 and x is equal to 2. So when x is 0, we just plug it into the original curve. That becomes 2. Yep, it's just 2. So that becomes 0, 2. And when y is equal to 2, sorry, when x is equal to 2, my bad, then y is equal to 2 plus 6 minus 8. 2 plus 6 minus 8 is equal to 0. So it becomes 2, 0. Now, looking at this, we can just like make a sort of table. So we have our x values and our y values. So 0, 1, 2. Those are our samples. So when x is 0, y is 2. When x is 1, y is 4. When x is 2, y is 0. So this looks like it's going up and then going down, because the y value is increasing up to 1 and then it's falling again back to 0. So this looks like it's a maximum because it has a positive gradient from 0 to 1 because it's increasing, the y value is increasing, but has a negative gradient from 1 to 2, so it's decreasing there. So we can say that 1, 4 is a maximum. You can kind of visualize in your head. If you have like a maximum like that, then it's an ascending gradient like that, getting larger and larger, and then it falls again after the maximum. Now we need to do the same thing with the other point, -1, 0. So we can make a graph again and take points on either side of -1, 0. So we have -2, -1, and 0. Those will be our three things that we use. So when x is -1, we know y is 0. When x is 0, we already knew from the last one that y is 2. And when x is -2, well, we can find that out right now. So 3 times -2 is -6. So 2 minus 6 is -4. -2 cubed is -8, but that's negated, so it becomes +8. So we have 2 minus 6, which is -4, plus 8, which is 4. So over here, we see the opposite scenario. So from -2 to -1, it's decreasing because it goes from 4 to 0. That y value goes from 4 to 0. But from -1 to 0, the y value is increasing. So we can kind of look at it like this, where it's decreasing as it gets to the maximum, but then it increases after the maximum. So it's a minimum point we can infer. So, therefore, unlike 1, 4, -1, 0 is a minimum. So we've effectively just found the stationary points of these curves, and determined the nature. The nature is 1, 4 is a maximum and -1, 0 is a minimum. So in this curve, there are no such inflection points. However, let's go to one more example where there could be an inflection point. All right, so this is the last question of the video. We have to determine the coordinates of any stationary points on the curve y equals x cubed minus 3x squared plus 3x plus 4, and determine their nature as well. So first thing we do is take the first derivative, just differentiate once, which gives us 3x squared minus 6x, plus 3. And we have to now equate it to 0. And we can actually factor further to give an easier quadratic, which becomes, so that means that x is equal to 1. So there's only one stationary point on this curve, because that's the only thing that can make the first derivative 0. Also, I just want to explain why we equate to 0. So in our tangents and normal section, we differentiated it, and then we've used the x-coordinate to find the gradient. So in this case, we're finding the x value that will make the gradient 0 of this function. Because when we have a stationary point, let's say it's a minimum like this, the tangent would be a straight line to the minimum. Or if we had a maximum, it would be a straight line. But the point is that the gradient at that point is 0. It starts to change, and at that instantaneous point, it has no change. So I hope that makes sense. Anyway, it's not that important. You're not going to be asked why we evaluate it this way, but it's just good to know. Now we find the y-coordinate when x is equal to 1. So we just substitute that into the original equation, which becomes 1 minus 3 plus 3 plus 4. So 1 minus 3 is -2, plus 3 is 1, plus 4 is 5. So it becomes y equals 5. So our coordinates are 1, 5 for the stationary point. Now, what we have to do is determine its nature, because we found the point, we just don't know if it's a maximum, a minimum, or an inflection point. The way we do that is construct a diagram, a sign diagram. Well, a sign diagram, I don't typically like to write the actual sign, I just like to see how it's changing. So you can call it whatever you want, but usually people use sign diagrams. So we can have the x and y coordinates written out, and we take 1 from either side. So in this case, x is equal to 1 would be in the middle. Then we write the y-coordinate, and we checked using 0 and 2, the ones just next to each other. If you have a decimal for your x value, then just take the nearest whole number on either side. Okay, so when x is equal to 0, y is equal to 4. We can see because all the other x's become 0, but we're just left with the y-intercept, which is 4. And when x is equal to 2, then we substitute into y. that becomes 2 cubed, which is 8, minus 3 times 2 squared, which is 8 minus 12, which is negative 4, plus 3 times 2, which is plus 6. So we have negative 2 plus 6, which is 4, plus 4, which is 8. So, interestingly, we can see as we increase from 0 to 1, our y value increases as well. So the x value and y value increase together. So that means that in this case, the gradient is positive, increasing towards the stationary point, Then when you go from 1 to 2, we can see the y value is still increasing. So both the gradients of the points right next to the stationary point are actually positive. So we know that's an inflection point because it would look, and we know it would look something like this, because we have a positive gradient over here and a positive gradient over here. So it's like ascending upwards, and like the point would be around here somewhere. So that means that we have an inflection point. So that means on this curve, 1, 5 is a inflection point. So we've determined the stationary point coordinates and we've determined the nature of them. In the next video, I'll actually explain how the second derivative test works, where we differentiate again. We differentiate the differential of the original function and explain how we can use it to determine the nature of points much easier, and also explain its drawbacks. But for now, that's it for this video. Thanks so much for watching, and see you in the next one.